Hello. Today I would like to discuss something about magnetism and relativity. First of all, let us consider an infinitely long wire carrying a certain current I. We all know that there would be a magnetic field going like this. Dots here, crosses here. Easy enough. We also know that the current is due to the flow of electrons moving with velocity Vd in this direction. Vd is the drift velocity of electrons. Things are pretty simple here, but the question arises that what happens when I change my frame of reference? The observer, that is me, started moving with the drift velocity of electrons along with them. The question is, what will happen to the magnetic field, and will there be an electric field induced? When I asked this question to one of my friends, he said that because the current is due to flow of electrons and the observer is moving along with the electrons, he would see that the electrons are perfectly still. No flow of electrons would mean that the current is zero, and since field is directly proportional to current, hence field would also be zero. According to me, this theory is wrong. First, let us try to prove this wrong by using an observation. Say I have a compass needle here. Since it is in a magnetic field, it would surely show some deflections, and it would be a periodic motion with time period, say t, and this t is dependent on the magnetic field and the magnetic moment of this compass needle. Now, according to the theory of relativity, if we are moving at velocities much less than the velocity of light, then the time which we measure from any frame would be constant. Now, because time is constant, the time period of its oscillations would also be constant, and hence the magnetic field should be the same as observed by a stationary observer. What I mean to say is, the magnetic field should not depend on the motion of the observer. But let us say that my friend is right. According to him, the electrons are perfectly still. So let us consider case 2, wherein the electrons are still and the observer is also still for this case. But what will happen to the compass needle? Obviously, it would appear to move with velocity Vd in the opposite direction. So some of you may say that we can consider this line as an infinitely long wire having a charge density, linear charge density lambda. So for this compass, the electrons would still be flowing downwards, and hence this compass would experience a magnetic field, because since for this compass the electrons are moving downwards, the current would be moving upwards, hence it would feel a magnetic field. Perfectly fine. But there is a flaw in this explanation. We said that this wire was charged, but was it? We did not add any electrons, we did not remove any electrons, so how can we say that this charged wire is actually charged? A current carrying wire is in theory neutral. It does not carry any excess of charge which would cause it to be positively or negatively charged. Now, some of you may say that because there is no current, there would be no magnetic field, and hence the compass needle would stop showing deflections when we start moving with a certain velocity. That is, when we move with the velocity of electrons, the current stops and the magnetic field also stops, and hence what we would observe would be that the compass would not show any deflections. If we accept that the compass would not show any deflections, let us accept this for a moment, although it is not true, we can counter this. Now, since we know that the magnetic field, say a distance r from the wire, is constant, we can say that this is equivalent to this case, in which there is a constant magnetic field, and this magnetic field is also uniform that is with respect to space, and constant that is with respect to time. So this magnetic field, I'm not saying what source we have used. Maybe we've used a current carrying wire, maybe it can be a solenoid, or maybe I've just used a bar magnet. Bar magnet would be better here. Maybe I have used a bar magnet, a combination of bar magnets, to get a uniform magnetic field. There are ways to get uniform constant magnetic fields. So let's say we have a uniform constant magnetic field, and then we have a compass here. Now if we accept this theory, with what velocity should this compass move so that it stops showing deflections? For no deflections, what should be its velocity? It's pretty much absurd to even think that it would stop showing deflections. So this theory can be proved wrong here itself, because since we cannot find a particular velocity in which it would stop showing deflections, because there is no current carrying wire here, there is no electrons moving here, there is no drift velocity of electrons, so we cannot say that we can actually find a velocity for which this compass needle would stop showing deflections. By this time we can obviously say that my friend who had suggested that the magnetic field would be zero is obviously wrong. What I had said, that no matter what the velocity of the observer is, the magnetic field that he would observe would still be constant, because just by observation, because the time period of the oscillations of the compass needle were constant, so should be the magnetic field. A more concrete and better way to prove this is by imagining what the wire is actually composed of. In reality, it has protons also and electrons moving this way. So this would give us a current in this direction. Now when the observer, in this case the observer is still, but when the observer also starts moving with drift velocity downwards, what I see is the electrons are still, the electrons aren't moving. But what about the protons? They're not gonna remain still here. In this case, the protons would be the ones moving with drift velocity Vd, and this would constitute the exactly same amount of current as in this case. Hence the current never changed. Because the current never changed, the magnetic field is also the same in both cases. Hence, in my opinion, even the magnetic field observed would be independent of the motion of the observer.